A system of equations is a set of equations. They can have 2 variables, 3 variables. Some of your equations could be linear, quadratic. There's a variety of types of equations that a system can include. So today we're going to focus on a set of equations where they are both considered linear. That means that the exponent on the x and the y are both 1. We're also going to focus today only on solving a system of 2 variables, meaning only an x and a y. So a solution to the system is the set of ordered pairs that will make both of the equations in the system true. And there are a variety of techniques that we could use to solve a system. Today we're going to focus on the method of substitution. And so let's just look at a few different systems and how we would want to attack those particular systems using this technique. So for our first example, we are going to use the system, and this is how you write a set. You use a little bracket. We're going to look at the system where y equals 2 and x plus y equals 4. Now when you're using the method of substitution, what you're trying to do is you're trying to solve these equations, what x and y will make them true, but you want to focus your attention on trying to find where one of the equations is already what we call solved for one of the variables. In this case, we have one equation that already says what y equals. Y equals the value of 2. And so we're going to use that information and we're going to substitute that into our other equation. And so this is the method of substitution. Take the information from one equation and substitute into the other so you can start solving. And so what happens is this equation now looks like x plus 2 equals 4. So I want to replace the value of y with what the information from the other equation says y is equal to. And now when I solve, I get the value that x equals 2. Now our solution has to be an ordered pair. I need to know the value for x and I need to know a value for y. But our system started out already telling us what y was equal to. So in this case, our solution is going to be the value of x equals 2 and y equals 2. And this is how you're going to write your solution. You're going to write it as an ordered pair. So if you come across a system where one of the variables is already basically giving you the answer, there's just a straight number, a constant, you already have part of your answer. But you're going to use that information in the system in the other equation to solve. So let's look at what happens when that is not just the number 2, but it's an expression. So let's look at the system. We have y equals now 3x. And then the other equation is going to be a 2x plus 4y equals 28. So now I do have that what y equals, right? So but instead of y equaling a number, right now we have what y equals as an expression. So I'm going to have to take this entire expression, what y equals, and substitute again for the variable y. So what I need to do is I need to plug or substitute this whole expression in for that variable. And when I do that, I'm going to leave everything else alone. So 2x plus 4, but now instead of y, I'm going to replace that with 3x equals 28. So I'm replacing y with the expression that the other equation tells me y is equal to. And when you do this, the whole purpose is that now I have an equation with just variable x and constants that I can solve. And so we've got 2x plus a 12x equals 28. And then I can combine my like terms here on the left and divide by 14. And so now I know what x equals. So when I start thinking about how am I going to write my solution, the value for x is 2. Well, I can't say what the value for y is yet. I can't say y is the value 3x. I need an actual coordinate or a number. So what I need to do now is I need to come back up here and say, now that I know what the value of x is, I can substitute back in for y. So that way the y value is 6. And so this would be the solution to my system. This is the x and the y coordinate that would make both equations true. And you can check. If I plug a 2 in here for x, the value for y is going to be 6. And you can do some work off to the side if you really want to check that if I plug in a 2 here and a 6 here, that the value is going to be 28. I mean, 4 times 6 is 24 plus 4, and that is 28. So we can kind of do a mental quick check that this is going to be the answer or the values that would make both equations true. And so as we start moving on, some of the examples are going to get more difficult, but it's going to be a variety of what you're going to see. So for example, let's look at the system x plus y equals 5 and x equals y plus 1. So now again, when I look at this, I'm trying to always look for either an x equals or a y equals. I'm trying to find if one of the equations is already solved for one of the variables. And we consider this equation to be solved for x because it says x equals this expression. Right? So I'm going to have to replace that whole expression in for x. I almost did it for y, but I need to replace it for x. And so what that's going to look like is in this equation right here, instead of it saying x plus y equals 5, I'm going to replace x with the expression of y plus 1. And that's my substitution for x, plus the y that was already there equals 5. So this y equals 5 is still part of my equation. I'm just replacing my x with that expression. Now again, our goal is to solve this equation. When I combine my like terms, I get 2y plus 1 equals 5. Then I'm going to move the 1 over to the other side and solve for y. And so now I know what y is. Again, we can go back into the expression where it says x equals y plus 1 and resubstitute to get the value for x. So now my solution is when x equals 3 and y equals 2. So you can see that the process is relatively the same every time. Probably the most complicated that you're going to come across in terms of substitution would be ones like this. So we'll just do one more, and then we're going to talk about some special cases. So we have y equals minus 2x plus 13, and we have a 4x minus a 3y equals 11. Now again, I do have an expression where y is solved, so I'm going to use that. Now this one is going to be a little bit more extensive because this whole expression needs to go in for y. So let's look at that. All right, so off to the side here, I'm going to keep my 4x and my minus 3. But I need to replace this whole y with that entire expression of negative 2x plus 13. And it's really important that you put parentheses around that expression, because in this expression, the negative 3 is being multiplied times y. So if this is my expression for y, I'm going to need to put parentheses so I can distribute correctly. If you don't put parentheses, usually you don't distribute this negative 3 correctly to the value or the expression of y. And so we have a minus 4x. The negative 3 times the negative 2x makes this a positive 6x. Negative 3 times 13 is a negative 39 equals 11. And again, I can combine my like terms. And now when I move 39 over to the other side, I'm going to get 10x equals 50, or x equals 5. So again, part of my solution is when x equals 5. And I need to go back up into this expression up here, and I'll just show my work off to the side. Negative 2 times 5 plus 13 is going to give me a positive 3. And so the other portion to my coordinate is 3. Now these are pretty much the examples that you're going to come across, the types of problems you have to work on. And we do have what we consider a few special cases. And so we'll just go over those really briefly. So special case. So let's just look at the first one. Alright, so we've got 2x plus y equals 3. And I have an 8x plus 4y equals 6. Now the first thing you want to notice is that you don't have any equation that says x equals or y equals. However, this first equation right here has a 1 as the coefficient on this y. So what I can do over here off to the side is I can actually solve this for y first. So if I move the 2x to the other side, I can write this as y equals, and write this in slope-intercept form, where y is on one side and the x and the constant are on the other. And so if that happens, where you don't have automatically an x equals or y equals, you can solve the equation that has a 1 as a coefficient, so you can use it for substitution. And so now I'm going to substitute. I'm going to take all of this for y and plug that in. And so let's see what happens. I get 8x plus 4 times the value of y equals 6. And again, now I'm going to distribute. And when I combine my like terms, because these are opposites, I get 12 equals 6. Well, that's a problem, because all of my variables are gone, and I cannot continue to solve for x. When I try to solve for x, I get something that is a false statement. All of my variables disappear, and this is untrue. What happens when all of your variables disappear like this and you don't have a variable to solve for, and you get a false statement, this means that you have no solution. There is no ordered pair that would make this equation or this system of equations true. Right? It's a little bit weird, but it only happens when you eliminate all of your variables and you get a false statement. Now the other type of special case is very similar. For example, let's use 2x plus y equals 3 again. And let's try 4x plus 2y equals 6. So again, very, very similar. Again, I'm using this equation again for a purpose, because I want to be able to, again, use that technique of solving for y. And what's going to happen now when I replace all of this information with y, let's kind of look. I get 4x, again, plus 2 times the expression for y equals 6. And when I distribute, you're going to notice that something is going to happen. Again, my variables cancel. But I get down here, 6 equals 6. And that's a true statement. So again, all of my variables canceled, but I ended up with a statement at the end that was actually true instead of false. What this means is that you have an infinite number of solutions. All right. A solution to one equation is going to give me a solution to the other equation every single time. That's because we can't see it yet, but these is really the same line. It's just that it looks different, but if I were to graph these two lines, they'd be right on top. So every coordinate that makes this equation true also makes that equation true. So just keep an eye out for your special cases. Again, it only happens when all of your variables cancel and you're left with either a true or false statement. When that's not the case, when you can solve, you get solutions that are coordinates.